Hello everyone, welcome to Coding Decoded. My name is Sanjay Dodeja. I'm working as Technical Architect SD4 at Adobe, and today I'll be explaining you the underlying concept behind DP on trees. So if you are not aware of this concept or you feel that it's too complicated, after going through today's video, you yourself feel that it's a cakewalk for all of you guys. Without further ado, let's get started. So when I say dynamic programming, what are the two approaches that you have always used to solve any question of dynamic programming? The first one is top-down approach, the second one is bottom-up approach. I think most of you are already aware of it and I don't need to reiterate, although in case you are not aware of it, I'm attaching the playlist in the description below, so do check this out. Now let's get started. And what approaches do we use to solve this question using the top-down approach and the bottom-up approach? So it's really straightforward. In each and every problem of top-down approach, what do? We use recursion plus memoization, and in the process of finding out the answer, usually we either have to look out for the maximum value or the minimum value of across all the possibilities specified in the question. So we recursively iterate through all possibilities and we use memoization so that we are not recalculating those values that we have previously calculated in the past. This forms the basis of top-down approach. And let's talk about the bottom-up approach now. In bottom-up approach, we start building the matrix from the ground level 0, and we iterate over till the given subset of the problem, given input data set. And while iterating and building the answer up till the length of the given input, whatever value remains in the last becomes our answer. So this is a typical approach that we usually follow. Now let's talk about tree. And when I say tree, what kind of traversals are you guys aware of? The first one is the recursive way. I call it DFS, and under DFS, three possibilities occur. The first one is the post order traversal. Let me just signify it with left, right, info. The other one is in order traversal, left, info, right. The third one is pre-order traversal, info, left, right. The other way to iterate over traversal is iterative way, and under iterative way, two techniques come into picture. The first one is the BFS level order traversal, and the next one is Morris traversal, in which we usually use stacks. Now let's get back to the problem statement, DP on trees. And whenever you think that DP on trees would be applied to any question, that simply signifies what you need to do. You need to go for the top-down approach. That simply means you will be using recursion. Along with this, you will be using memoization. And when I say recursion on trees, what does come to your mind? It is very simple and straightforward. The post order, in order, and pre-order traversal. And how do we achieve memoization? Again, we can either use a map wherein the key of the map would be node and the integer value would be the minimum or the maximum value corresponding to this node so far that you have seen while traversing through the tree, or you might not actually need it. You can simply store it in a global max or min variable and find out your answer instead of identifying the local value of your min or max value for each node. So there are two options available. I'll be walking you through both these options by a test case. So let's quickly understand the question first and then see DP on trees live in action. The problem statement that I have chosen to understand DP on trees is binary tree maximum path sum. It's a hard level on Leet code, but I don't feel the same. As per the question, we need to identify the maximum path sum that exists in your binary tree. Also, it is given that the path may not include the root of the binary tree, and it can start from any node of the binary tree, it can end at any node in the binary tree, but the path should not break. So let's walk through few examples and understand it. The maximum sum path in this case would include 1, 2 and 3, all three nodes, and the total sum would be equal to 6, and this would be the answer including all three nodes. And let's walk through the next example. Here the maximum sum path would be 15 plus 20, 35, 35 plus 7, that gives you 7. So this path would lead to the maximum sum path. However, in case if you argue with me, what about this particular path? Here you will see that the value is less than 42. So 9 plus minus 10 is minus 1, minus 1 plus 20 is 19, 19 plus 15, let's go for 15 over 7, then you will get 34. 34 is less than 42, as a result of which that path gets rejected. Now comes the question, how can we solve this up? So we will be using DP on trees technique, and once I'll tell you this technique, you will yourself see that it gets applied in each and every question that have been highlighted over in this playlist. So after going through this solution, what do you need to do? You need to try these questions up. I'm attaching the link in the playlist below, so do check this out. As per the question, the path can start from any node and end at any node. So I've taken a slightly different example, and let's talk about the maximum sum path that exists in this tree. That path would be equal to this one that I am just highlighting right now. And the total sum would be equal to 9 plus 15 is 24, 24 plus 20 is 44, 44 plus 7 is 51. So the answer for this particular tree would turn out to be 51. Now comes the question, how will we iterating through this binary tree? It's really simple. What do we need to do? We need to identify the left max path while traversing over the left subtree. We need to identify the right max path while iterating over the right subtree, and what would be the current max path containing the current node. Remember, what would be the maximum path sum containing the current node? It would be equal to the left path max plus right path max plus node value. So whatever value you have identified from the left subtree, whatever value you have identified from the right subtree, you add these two up and then you add it to the current node's value to identify the maximum sum path containing the given node into consideration. If you are able to think this much, then 70% of the algorithm is done. There is a small corner case that we need to think of. What is that corner case? Let's walk through an example. So let's consider you are given a binary tree wherein the root of the tree is -1, the other two elements is -2 and -3. So if I ask you guys what would be the maximum sum path that exists in this binary tree, it would be equal to -1 itself, and no other subchild would be considered. So while considering the maximum sum path from the left subtree or the right subtree, if the value goes in negative, then you should set it to 0 value. For example, as in this case, what would be the maximum sum path for the left subtree? It would be equal to -2. Since it goes in negative, let's cap it to 0. So because that will simply means we will not consider this path. Similarly, here in this case as well, the maximum sum path coming from the right subtree happens to be -3. Since it's negative again, we should cap it to 0. And once we have this, the maximum sum path from the left subtree and maximum sum path from the right subtree, which in these two cases come out to be 0, then we will add it to the current node and the total sum would become 0 plus -1 plus 0, that turns out to be -1, and this is in sync with our expectation. So far so good. Let's talk about the final case now, the final algorithm. Now let's apply this entire algorithm onto this given binary tree and see how values are getting populated. So you're currently at the root, which is -10. So the first thing that you need to do, you need to identify the maximum sum path coming from the left subtree. Here in this case, we will first invoke recursively on the left subtree and find out the maximum sum path corresponding to 9. It would come out to be 9 itself. So 9 gets returned from here. Similarly, let's calculate the maximum sum path coming from this particular subtree, and let's start the iteration recursively. So this time 20 would be considered as root, and first of all we'll go in the left direction followed by the right one. So we'll find out the maximum sum path coming from this particular node, and since 15 would be treated as the current root now, we will again recursively invoke the first on the left subtree followed by the right one. So here we see only one node, which is 9. It is greater than 0. That simply means the maximum sum path coming from the left subtree happens to be 9. So 9 would be returned from this, and similarly 5 would be returned from this. Now comes the most interesting part. So the maximum sum path containing 15 would be equal to 15 plus 9 is 24, 24 plus 5 is 29. That means the maximum sum path containing this particular node happens to be this one, which is absolutely correct. Corresponding to 15, what is the maximum sum path? It is 29. Now comes the concern, what value will be returned to the calling parent? So far we have appropriately calculated the maximum sum path with 15 acting as a juncture, because at 15 one way chosen is towards the left and other way chosen is towards the right. Now comes the concern, what value will be sent to the parent of 15, which in this case is 20. And if you are traversing from 20, you go back to 15, and at 15 you can only choose either the left subtree of 15 or the right subtree of 15. So which one are you going to choose? You will be choosing the one that have maximum value. So that simply means you will go for this particular path, 15 plus 9, which is 24, as a result of which you will be returning from this particular node or subtree 24 value to the calling parent. So 24 gets returned to the caller. So the value returned to the calling parent is equal to the node's value. So let's call it node.val plus maximum of left subtree comma right subtree, left max comma right max. So this is the formula for it, and this is specific to this particular example, not everywhere. So here the node's value is 15 and the maximum value of left max comma right max is 9. So 9 plus 15 gives you 24, as a result of which 24 gets returned. So let's do the same kind of thing for the right subtree of 20. Let me just change the color of well, and the right subtree of 20 is this one. So the call goes over here and we will be calculating the same kind of stuff again. So let's go to the left child. The value is -4 since it's negative and it's a leaf node. -4 will be returned to the caller. However, since it's negative in nature, we will cap it to 0. So 0 gets returned from here. Similarly, from here as well, 0 gets returned. Now, one possibility of maximum sum path containing 7 as the juncture is equal to 7 plus 0, which is 7. Since 7 is lower than 29, we'll ignore it up. And what value will be sent to the caller, the parent of 7? It would be equal to the maximum of 0, 0, which is 0, plus the node's value, again that is 7. Now from the left subtree the value comes as 24, from the right subtree the value comes as 7. So let's consider the maximum sum path where 20 is acting as the juncture. It would be equal to 20 plus 24, it is 44, 44 plus 7, it turns out to be 51, which is in sync with our expectation. So if you add these three numbers up, you will get 51, which is again was expected, and the path would be something equal to, let me just highlight that up, and it will have this node, this node, this node, this node, which is again in sync with our expectation. And let's continue the process. What value will be returned to the parent of 20? It would be equal to 20 plus the maximum of 24 comma 7. What is maximum of 24 comma 7? It is equal to 24. So 20 plus 24 gives you 44. So 44 will be returned to the caller of the parent of 20. And let's do the same thing again. Even before that, here at 20 the maximum path sum turns out to be 51. So we will replace 29 by 51, which tells us the maximum sum path so far traversed across the entire tree. Let's get back to the root of the binary tree, which is -10, and let's see what value was returned from the left subtree. It was 9. What value further is returned from the right subtree? It is 44. So 9 plus 44 is 53. 53 minus 10 is 43. So 43 happens to be lower in nature than 51, as a result of which the maximum path sum value will still be remained as 51, which is again in sync with our expectation. And with this we have completely traversed over the binary, so the binary tree that we had. Now let's quickly walk through the coding section, and while doing so we will be creating the template for DP on trees that gets applied to every such question. So let's get started. The first thing that I have done here is define a maximum value, initialize it to minimum 1, so that whenever I find a better value than this one, I am able to replace it, and the default value initialize it integer.min value. Since in the question we are interested in finding the maximum path sum. Moving ahead, I have created a map, and here the map key is tree node comma integer. So the key represents the current node acting as the junction, and the maximum sum path is the value corresponding to this given constraint. I've initialized it to a hash map. Moving ahead, I have created a helper method DFS, which is basically iterating over the entire binary tree. in a recursive fashion, and once that traversal is done, I simply return back the maximum value stored in this variable. The problem reduces to writing this DFS method appropriately. So the first corner case that comes to everybody's mind is to check whether the node is null or not. If it is null, then what do? You simply return 0 from there and then itself. Otherwise, you go ahead and create two variables, left max path and right max path. Both of them are initialized to 0, 0. And in case you check whether there is a value already computed in the past corresponding to node.left. If it does exist in your map, you simply retrieve it up. So this is the memoization logic that I have written. And in case it doesn't exist, that means you are computing it for the first time. So you go in a DFS fashion and you pass in node.left to it. And don't forget to cap it to 0 in case this value goes in negative. So math.max 0, DFS of the node.left is taking care of capping this value to 0 in case this value comes as negative. Otherwise, in case this is positive, then this would be preferred. Once we have done that, we again do the similar kind of thing on node.right, the right subtree of the current node. So in case the map already contains this value, you simply extract it from the map. Otherwise, you again recursively iterate over node.right and recursively pass the DFS method again. Moving ahead, you calculate the maximum path sum wherein the current node is acting as the junction. So the total value would be equal to left path max, right path max and node.val. You have this value as one of the contender for your answer. You compare it with your maximum value, and once you have selected the maximum one out there, you simply put this value in your map. So map.put node, val. Once we have done that, what do? We need to return some value to the calling parent. And what that value would be equal to? It would be equal to node.val plus math.max left path max, right path max as showcased in the presentation. So let's quickly submit this up. Accepted, 10 milliseconds. It is 5% faster and it is slower in nature by virtue of creating the maximum path sum for each and every node. Although it wasn't needed in the question, but we still did it so that you guys get a better clarity on how things are operationalizing across the traversal. Now comes the concern, how can we create the template out of it? Selecting the max value or the minimum value depends upon the question, whether the question is asking you to go for the maximum path sum or minimum path sum, and you can appropriately set this value depending upon the question's requirement. Now comes the concern, writing the DFS traversal appropriately. It's pretty much the same. You check for the corner cases. If node is null, you simply return 0. Otherwise, you iterate over the left subtree, you iterate over the right subtree, and capping to 0 is something specific to this question. It might not be needed in each and every question. Once you have those left path max and right path max, you calculate one possibility of answer for current node into consideration, which in this case comes out to be left path max plus right path max plus node.val. Once you have it, you compare it with your global max variable and select the one that is of higher value overall. Once you have done that, you put this value back into the map. So this will be part of the template. This will depend on the question's requirement. And what value is to be returned from back to the calling parent is again dependent on the question's requirement. So these two statements will depend upon the question, and DFS will be done on the right subtree and the left subtree. So this is pretty much the same. Rest of the DFS traversal is the same. So what is changing? This statement is changing. Line 33 and line 37 is changing. The rest, the template remains the same. With this, let's wrap up DP on trees concept, and I explicitly chose a hard question so that you get a good hold of the underlying algorithm. And it's time to With this, let's wrap up DP on trees concept, and I explicitly chose a hard question so that you get a good hold of the underlying algorithm. Now it's time for you guys to apply DP on trees template onto these 4 questions, and it will give you enough confidence that you can crack any question of the same concept whenever you face it in your future interviews. With this, let's wrap up today's session. I hope you enjoyed this video and the template, and if you do, then please don't forget to like, share and subscribe to the channel. Thanks for viewing it. Have a great day ahead and stay tuned for more updates from Coding Decoded. I'll see you tomorrow with another fresh question, but till then, goodbye.